I'm glad to finally meet the group. Yes, because I've been working on agent-based models for 10 years now, and I've heard about the famous agent-based group here at Mason. So here you are, guys. Good to meet you. So yeah, my background is applied math, and I spent 9 years at Argonne building agent-based models for transportation.
How long have you been here, Vadim? How long have you been at Mason?
This is my 4th year. I moved here 3 years ago. So here's the model that we built at Argonne is called Polaris. So it started. We got a big grant from US DOT to develop a simulator, and our first reaction was, okay, we're going to take an existing ABM model and going to retool it. And since we were at Argonne, we worked with Repast team. We took Repast, and we had many meetings with the Repast team, and we realized that to retool Repast probably is going to be less work to rewrite things from scratch. And the reason is because transportation, there's a lot of very specific operations you do in transportation and very specific things that agents do in transportation, and pretty much none of them existed in off-the-shelf tools. I can give you a sense that 80% of the computations go towards computing paths on the network. Mm-hmm. So if your agent-based modeling tool doesn't have a fast path calculator or calculator flexible enough for transportation, because a lot of nuances in how the paths get calculated on the networks. They're like turn restrictions, they're lane use restrictions, time of day restrictions. So the path calculation algorithms need to be very sophisticated. So your off-the-shelf fixed routing won't do what you're trying to do. And then calculating transit paths become an even harder problem, even more time-consuming. And since this was like the core of the operations, we decided, okay, we're just going to do things from scratch, and we started by building this Polaris tool. And we worked closely with Repast team while doing that. So this is the outline of the tool. So it's a transportation simulator. If you guys are familiar with transims, so it's basically the next generation of transims. And it is the same program at DOT that funded transims that funded our work at Argonne. And we worked with the original transims developer while building this tool. So it's basically, so we model each individual traveler, and each individual traveler goes through the day and makes the decisions. Decisions involve departure times, destinations, types of trip people want to do, and then we simulate the infrastructure, the road infrastructure, traffic lights, highway network and transit networks. And the goal is basically to see how specific transportation management strategy or transportation policy affects congestion patterns on the network. So our main goal is to simulate congestion patterns. And since we were DOE lab, we also got some of DOE money to do energy analysis of the transportation networks. So we also had a piece that analyzed the energy part of it. So this is outline of the Polaris. So we calculate the plans, who goes where at what time, and then we execute those plans in the network. So see how those plans propagate to the network and how congestion forms as a result of that. And the scale of the problem is millions of people and tens of millions of trips. To give you a sense, Chicago model was our first model that we built. We had 9.5 million people. It's a Chicago metropolitan area, and those people do 28 million trips in one day. So we have to basically take 28 million, times and route those people through the network, and they make decisions while they go through the network, and they recalculate the paths iteratively. So this is a little bit set up for my talk. Is that we basically have some simulator phi. In our case, it's a transportation simulator, but you can bring your favorite simulator here. And we have two set of parameters, x and theta. X are the parameters that we're sure about and know, and theta parameters that we're not sure about. Okay, so in transportation context, theta can be sensitivity towards tolls. So how people react to the change of the tolls. Okay, so this is something we can kind of get a good guess from the survey. But the problem with those models, you get good guess from surveys, and then you put things into the model, and the outcomes still don't match the reality. So you have a lot of good guesses from different surveys, from different data sets, then you combine those good guesses into one model, And when you integrate everything together, the output of this model doesn't match what reality actually has. Okay? So it means, each of those guesses, might be a little bit inaccurate, but when you combine a lot of inaccurate things together, and then you propagate it through time, so those little inaccuracies actually blow up, and you start having something that gives you very, very unreasonable predictions. Okay, and in transportation we care about predictions. So I know in this group you guys care about more like generating insights. In transportation it's all about predictions. Can you predict traffic flows or not? Because all the policy making based on making good predictions. They want to know exactly how flow is going to look like if this new piece of infrastructure is built, or if we implement the stalling policy of this happens. So they know exactly what they want to know is how the traffic flow is going to look like. So prediction is kind of the gold, and that's what we care about. Okay. So this example of another network, Detroit model, it has 28,000 road segments, 50 million trips. It happens every 24 hours. And each run of the simulator takes hours to days on a fast desktop. And the parameters data that we try to understand, they're usually highly sensitive and high dimensional. And when I say theta, so what type of analysis we want to do? One of the main problems we care about is calibration. So some estimates of the state are going to come from surveys or from good guesses by engineers, and then they don't match the reality. So you have to go back and adjust those good guesses to make it even better, right? So this process is called calibration, and you guys are probably familiar very well with the process. And so we mostly care about the calibration, and all the work that they're going to present is motivated by calibrating those simulators and finding the good values for those states that lead to sensible predictions.
What's your time step in these types of in this model? Is it like every 5 minutes, 1 minute?
So for traffic flows, it's 6 seconds, which means like your traffic signal have to be multiples of that. And for a demand model, it's every minute. So you can change your decision on the departure time or route that you take every minute in the simulator. But your vehicle, when it gets propagated through the network, every 6 seconds will update the physics of the network. I can show you a little bit about, the Polaris GL is actually a visualizer for Polaris. That's a tool that was developed here at Mason. If my internet is fast enough. ED-ROM, let me see if I can go to Mason Secure. It's a web-based tool, so I cannot do it offline. But while I'm waiting, maybe I'm just gonna go back to slides. I'm not sure if, I cannot connect for some reason. I can go back to ED-ROM, let it connect. Anyhow, so maybe at the end we have time, I'll show you a few visualizations of how the simulator works and what exactly we produce with it, okay? So a little bit of run times, right? So models really care about run times also. So minutes is good, you can do things iteratively in real time. So one of the things those simulators use for is real-time traffic management. They're not used at this scale that we develop, but smaller simulators used for traffic management in corridors. So when you try to understand how to assign ramp metering or how to assign the tolls, you can use those simulators and you can predict the results of it, and you basically have this model predictive control type of setup. Few regions in this country use it, and few cities in Europe do that. So you cannot do it with regional simulators. You can do it with smaller network that only understand a small part of the network. So hours, it's very hard to achieve to do hours on the regional simulators. And so that's one of the goals was for us at Argon is to do it in hours, and we were able to do it just by using a lot of C++ hacks and parallelism. Okay, so we can simulate in hours. This is the status quo in this field, so it takes days to run those simulators, and it's okay for planning organizations. So if you try to build 2015 prediction or 2050 prediction, then if it takes 2 weeks, it's fine. But again, if you try to calibrate this model, those few days run is not something. And if you do research, right? So imagine you want to test a new idea, and you have to wait for a few days for a simulator to finish. It's going to be it's going to be long PhD theses. And months. Actually, some of them run months, but it's unacceptable. But we live in this regime, and we're trying to move this regime. But still, it's very slow. Even if it's ours, it's very slow simulations.
But you talk about runtime. Just go back. I was probably not going to go on the slide about this. Just give us a quick version of how much data is required to set up a model in Polaris for a new city. And can you meet GIS layers, or do you have to do it all kind of by hand? Or what's the
Yeah, so you can recycle a lot of the OpenStreetMap data. And OpenStreetMap gets better. So we need lane numbers, we need facility types, and we need connectivity records that are usually missing in the OpenStreet data. So we need to know exactly which lane connected to which lane. And we need, if you want to have a more detailed simulation, you need traffic signals. So just by bringing those details into the model takes a lot of time. So besides the geometry of the road, you need some features of the road. It takes time. Bringing transit into the model became easier with GTFS, with the Google Transit feeds. So it's became a standard. Basically, all of the transit agencies in this country have their transit data represented in this format. So once you know how to read it in and convert to your model, you can get any region very fast. Getting demand data and understanding travel patterns. This usually comes from surveys. Surveys actually are usually run by metropolitan planning organizations. In Chicago, every 5 years they go and interview a few hundred people, asking them to fill in diaries. And so you have this nested logic models, multinomial logic models, basically choice models, fit into this data, and that's how the decisions that get represented. It's this econometric model, the same models that use in marketing. That's how travelers make decisions about destinations and types of the trip they want to make. So data is there, but there are a lot of this, still a lot of hand tuning that requires. Okay? So the question is how we can improve on this problem of high dimensionality and long run times, and the solution that we're working on is build approximators. So rather than using the raw ABM model, can we build an approximator to it? So at least surrogates is another term for it. So we can reduce the run times from hours to minutes. And that's going to be huge help to the modelers, people who do it in the field. They want to do this, quick analysis, so like dirty look at what happens if we do this, and this, and they can, if they can build approximators, good. Another reason why we want to build approximators, if we want to run some type of uncertainty quantification analysis or optimization algorithm on top of the ABA model, then again, waiting for hours for this model to be executed is unreasonable. So if we want to automate this inference process about the parameters of the ABA model, we have to run it fast. And reduce dimensionality. So again, if you try to understand, for example, optimal set for your parameters, if you try to calibrate, then you have to explore the input space. And if your input space is high dimensional, it becomes, you deal with cursive dimensionality. Exploring those high dimensional spaces becomes a very hard problem. So you want to reduce dimensionality. Just building approximator doesn't work, because even if you have something you can run fast, but you live in high dimensional space, even faster in times won't save you. Just this cursive dimensionality kills. Even if you can run, this very fast, exploring high dimensional spaces of inputs is very hard. Okay. So here's basic setup. We have a simulator file. We have parameters data that we're trying to understand. We observe some field data. You remember in our case, prediction is the main thing that we're trying to capture. So this simulator predicts something, and this is what we observe in the field. Let's say it's traffic flows, and we can get traffic flow data from the sensors or from the vehicle probe, so this data exists. And we have some uncertainty associated between this relationship, what simulator predicts and what we see in the field, and this uncertainty comes from inaccuracy of the simulator and measurement errors. So we have two types of errors here. Okay. So inaccuracy of the simulator is usually very hard to model, and we kind of take this part and put everything into one term, so we assume it's just one big, measurement error term, because this one is hard to quantify. Okay, and basically our simulator is just a stochastic process, and we're going to build a surrogate for it. I'm probably going to skip this slide. And to build a surrogate for the model, so I'm going to be talking about surrogates now. To build a surrogate, we use Gaussian process. So what is Gaussian process? Gaussian process allows you to, biggest advantage, it's basically glorified piecewise polynomial fit. Okay, so that's all it is. It's a piecewise polynomial fit, but it comes with a good property. It comes with this uncertainty quantification property, meaning that it tells you where your model is uncertain about the predictions. So the regions where you have large variance in the outputs as a function of the inputs, your model will tell you that, okay? And what you can do the sequential design of experiment, meaning you can run your simulator at the values of input parameters, which gives you, basically try to maximize the value of each run. So instead of just doing the latent hypercube and trying to, just cover the space of inputs with, random samples, you try to be a little bit smarter about how you sample the input space. And you can do it, it's in machine learning, they call it active learning. So you run at few locations, then you see how your surrogate does fitting those locations, and then you go back and you say, okay, I'm uncertain here, so I'm going to try again here. And you can have some objective function that tells you how to continue sampling the space. So if it's a try to minimize the loss, it's one type of way to explore the space. So designing, so there are multiple ways how you can explore the input space, but this notion of uncertainty in the surrogate gives you this opportunity. I'm going to give you a quick example of how the Gaussian surrogates work. I'm going to show it in a very simplistic simulator. This is my taxi example. So I have a grid, and I have bars, the red bars and blue bars that represent demand and supply. So how many people want to depart from here, how many people want to come to here. So this is those are my trips. And I operate a fleet of taxis, and I try to maximize the profit. And the only parameter I want to play with is the number of taxis. Okay, so I have two small number of taxis. People will have too long of wait times. They'll get frustrated and will walk or take a bus. If I have too many taxis, then I have to pay salaries to the drivers that don't do anything. Okay, so I have a lot of idle trips. So there is a balance between those two, and I want to find the good solution. So what I do, I basically try it at extreme. So I say, okay, I'll try and evaluate the operations of my system with 10 taxis and 90 taxis, and then I'll try something in the middle. I'll try with 30 taxis. So I pick 3 different setups for my model, 3 different values for my inputs, and then I basically try to predict the relationship between the number of taxis and the profit that I generate. And the profit is evaluated by my simulator. So I basically put those number of taxis, they run in the simulator, and I calculate my losses and gains. Losses, I pay for idle trips, and gains, I have passengers that pay to me. Okay, so those, I evaluate my simulator at 3 different locations, 10, 30, and 90. And then I build my surrogate. So what you see, the black line is the mean. So this is my piecewise polynomial fit into the response surface, if you wish, associated with the simulated values. And the gray areas, the blue areas, represent uncertainty about predictions. So which basically, what my surrogate tells me, if I want to know what's going to be my profit at 60, okay, I'm going to put my point on the black line, but it also tells me there's a huge uncertainty about it. And the reason there is huge uncertainty because there is nothing in between. So my model tells me, if you want to understand your profits at this level, you have to evaluate a simulator at this location. And that's what exactly I do, right? So my model, my setup here is I want to minimize the variance of my prediction. Okay, so, and my model tells me, okay, if you want to minimize the variance, sample here, get your simulated value here, and I do that. I evaluate at 65, and then it says, okay, go to 40 and evaluate at 40. I do that, and then it says, okay, evaluate at 40. Then evaluate at 50, I evaluate at 50, and then at some point I say, okay, I'm certain enough about my surrogate that I can actually use my surrogate for optimization, for example. In this case, you remember I'm trying to solve optimization problem, I'm trying to find the number of taxes that maximize my profit. And I'm gonna solve this optimization problem by using my surrogate. I have surrogate that is accurate enough. I know that because Gaussian process gives me uncertainty bounds on the look, there is certain bound here as well. Even though I evaluate my simulator at this location, I still have some uncertainty bound. And this uncertainty bound can affect that my simulator is stochastic. So dealing with stochasticity in simulators it's actually a complex issue. Okay, it's not easy to deal with stochasticity. And what might happen is you might evaluate here, you still might have a huge uncertainty about. So you basically then you have to decide how many times you want to sample at this specific design or this specific location to reduce uncertainty. So just by, those problems with stochastic simulators, you have to repeat the experiment at the same location multiple times, okay? We don't do that here, because this is just one-dimensional case and things become very clear. So here's a little bit more sophisticated example. It's not agent-based simulator anymore. It's actually a physics simulator. So we have this strontium-90 transport simulator, and it was collected from the Kurchatov Institute reactor radio waste disposal. And this model has 20 inputs: hydraulic conductivity, transversal dispersity, volumetric distribution, and we evaluated the simulator at 300 locations. So you have 20 inputs, and you evaluate the simulator at 300 locations. And now we try to build the Gaussian process surrogate for that simulator. So what you see, this is my y, the actual y, and this is y hat, something I predict from by the Gaussian process simulator. And what Gaussian process simulator learn is just the mean. Okay, mean is okay, but I don't need to build sophisticated learning machine to predict the mean, right? I can estimate the mean. It also gives me this huge uncertainty bound about this mean. So it's being honest. It says this is my prediction, and I'm very unsure about this prediction anywhere. So it basically honestly tells me about that. So this machine, this Gaussian process machine, becomes unusable in high dimensions. Actually, to be specific, it starts breaking at around 10 to 15 dimensions. Okay, it gives you huge flexibility. It's a very flexible learning machine, but it's very unusable in high dimensions. So that's the problem we faced. We started using those Gaussian process, doing 10 parameters at a time. We got excited, and then we started scaling it to larger sets of parameters, and this machine started failing. This is a little bit philosophical, but that's basically what happens with in high dimensions. So Gaussian process, and pretty much any flexible learner that you might know, is some type of nearest neighbor learner or kernel-based learner. Okay, kernel-based means if I want to get prediction for the new location, what I'm gonna do, I'm gonna look at my neighbors around me, and I'm gonna assign them weights, and they're gonna sum up prediction, values of those locations, and I'm gonna take the weighted sum of those. So that's what kernel-based machine does, or nearest neighbor does. And what happens in high dimensions is basically this is a little example. I take the 50-dimensional ball that generated 1,000 samples, and then project it 2 dimensions. You see what happens with uniform samples in 50 dimensions when they get projected in 2 dimensions? They collapse. Mm-hmm. So they collapse. It's somewhat counterintuitive. You would expect, the points to be uniform distributed in 2 dimensions, well, but they are not. Okay. So which means if you have high-dimensional space and you try to use any of those nearest neighbor approach or kernel-based approach like Gaussian process, and you try to predict for this location I'm going to have any neighbors, so your prediction is going to have basically useless and of very high variance. And that's what happens as your dimensionality grows. This is basically a histogram of the samples. So as your dimensionality grows, you see this is basically called concentration of measure. So you start getting concentrated around certain locations. In this case, it's 0. Okay. So the bottom line, it's hard to explore those high dimensional spaces. So this is another visualization, of course, of dimensionality in 20 dimensions. Even if you have a simulator that takes 1 second per run, okay, and you build a grid, you build your grid 10 points per direction. You'll have to run your simulator 10 to the 20, which is 3.1 trillion years. Okay, so making simulator fast does not solve the problem in high dimensions. Okay, so that's not the solution. Okay, and even if you try to evaluate the corners, you're going to have 10 to the 20 corners, and it will take you 12 days just to evaluate the corner points of your input space. Okay. And then you try to solve optimization problem, right? And you try to check for optimality, and even this becomes trouble. So you know how we check for optimality. We take current location, and we say, okay, try to go this direction and see if it goes up or down, right? If it goes up, means this is minima, and then you basically have to go and try to go in different directions and see if your function grows in those different directions. That's how we check for optimality, right? So there's going to be e to the 20 directions. Those pairwise angles greater than 60 degrees. Okay. So it's basically, if you try to go, in different directions, you basically will have to take that many directions, and even they will have 60 degrees apart. So just checking optimality becomes a very hard problem. So everything is hard in high dimensions, regardless of how fast the simulator is. Okay. There's a whole bunch of solutions in stats literature in applied math. You know, I come from applied math, but my recent work was more using stats techniques to address those problems. So one way is variable selection or variable screening. It's a very fancy term. Variable screening basically means I'm going to throw away some variables. I think they're irrelevant. Okay. Exploit model structure. If you think there is some additive structure, so this parameter does not affect this parameter, there's no interactions between them, then you can think of your model as additive. But once you have ABMs, it's hard to decouple it and write those additive functions. So it's like when you have some functions, you can do this, but in ABMs, you cannot do those things. Single index, basically, you assume that your value of the simulator is constant along certain lines or certain hyperplanes. Again, it works in certain physics problems, but I think it works in ABMs. Make simulator fast to parallelize. So, and we agreed that those solutions are not good solutions. Okay. So and this is field I'm coming from in applied math. In applied math, people write books about dimensionality reduction and how to deal with those complex math models. So one type is those linear time-invariant systems. You know, when dynamics of the system is basically is linear, and the dynamics doesn't change over time. So your A matrix is constant here, doesn't depend on T. And we know how to solve those problems very well. You know, there's balancification, transfer functions. This is technology. This is solved problem. We don't even think about this. The same applies to elliptical and parabolic PDEs. So if dynamics of your system is modeled by elliptical and parabolic PDEs, we know how to reduce those problems, how to reduce dimensionality of them. And again, this is like a solved problem. It's reliable, accurate. We have structure preserving techniques. It's computational cheap. So it's a technology now. It just works. We don't even think much about that. When we deal with this nonlinear stochastic dynamics, right? Xt plus 1 is just some ABM model of Xt. Then it's just the Wild West. I don't think anybody knows how. There's no good known solutions. And even there, like if you find a solution like we do, right, it's unlikely we're going to be able to preserve the structure of the model. And the error bounds, I'm very, I doubt that we'll be able to derive any meaningful error bounds like you can do in those two cases. So the state of the art, I think, in these cases, when you have this nonlinear stochastic dynamic, you have to agree on or accept something that works empirically well. And just, I think this is already a good achievement in this world. So trying to get some guarantees is maybe, a little bit further away, but at this point, we're just give some good empirical solutions. So that's what we're trying to do.
Before you leave that, I want to just mention the following. So this is the way I think many of us in the room think about the problem, et cetera, et cetera. And so normal to imagine wanting to do a good job on your last bullet there with the ABM model. Let me just mention the following totally bizarre thing that I had happen to me in the spring. So out of the blue, I get many ABM papers to review. Out of the blue, I got this paper from the Society of Petroleum Engineers, SPE, to be presented in April or something, about someone who said, well, we know how to do reservoir simulation. We know it's a Laplace equation, so it's one of the standard PDEs. Those are highly optimized simulators. Okay? They're used by the big companies to figure out how the reservoir works. Well, somebody said, can we do better if we not convert, not basically go ABM to math? They said, what if we say, let's have an ABM solve the oil flow problem in the reservoir? And they used a very simple kind of, I would call it kind of a percolation model. And they were getting like 100-to-1 speed up over the optimized PDE, which has been working on for 40 years, right? So it just struck me as very being wild that you could take a totally different approach to a problem and come up with a by the way, they were getting the same accuracy they got on their with this HMS.
Yeah.
So it's a kind of orthogonal way to think about some of these things.
But also, if they try to apply analysis for, if they try to get like error bounds on their solutions, given this new way of solving the problem, they probably will have hard time.
That's true.
Hard time doing that. So And again, I came from math to engineering. So in engineering, we think less about error bounds and guarantees than people doing math. But you guys work with policymakers. Policymakers might, well, I don't know. Anyway, maybe nobody cares about error bounds and guarantees.
People care, but people realize that many times you see how much power with it.
Yeah.
They don't know how to interpret it, right? I mean, they wouldn't know what to do with a confidence interval. They just want to mean.
Well, yeah, and in transportation, people just become very happy once you can replicate the ground truth. So, and as I said, this is gold standard. If you can replicate the ground truth, you become like, so you're in business. You don't really need to prove anything anymore. So if you can predict, you have a good model. That's the world I operate in. Okay. Okay. So active subspaces. I can say quickly. So there's this technique that came out in 2010. It's called active subspaces. The way active subspace works is basically applies principal component analysis to the contour plots of your function. So imagine you have a function that changes mostly in this direction but doesn't change much in this direction, right? So if you try to understand the sensitivity or do uncertainty quantification or do optimization, optimizing your function, you don't really have to explore in this direction. You only have to explore in this direction. Okay. So it's a good idea, and it has been shown to be effective in a lot of physics simulators. And the disadvantage of this approach is that it relies on calculating gradients. So you need to know the gradients to calculate those directions where your function changes the most. And another disadvantage of this approach is that it assumes some uniform structure. So it assumes some global structure in your function. Means that if you pick this direction is going to be the good direction regardless of where you are in the input space. Okay, and this is a contour plot from transportation simulator. So basically, try to see if we have anything like that. By we pick 2 random parameters out of whatever 15 we use as inputs. It's a small transportation simulator. And you see our surface doesn't look like that. So it has some structure here locally, and then it has different structure here, and then it has different structure here. So depending where are you on the input space, there's no unified local structure that tells you in which directions your function change. So this assumption that you basically can pick a direction and just work in this direction, in the ABM model, it doesn't seem a good idea, and getting gradients of ABMs is incredibly hard. So you can approximate again. You can get the surrogate of the ABM and then calculate gradients of the surrogate, but it becomes very unstable. And actually, we spent like a year of our life trying active subspaces before we gave up. So okay, and by the way, yeah, active subspace was like state of the art, right? If you go to applied math world, this is state of the art. So we're like, okay, we're gonna use state of the art. We're gonna apply it to ABMs, and we failed. Okay, so we're gonna say, okay, what's the next state of the art? And the next state of the art is neural net. Machine learners, convince everybody that neural nets can capture nonlinear patterns in the data, and they can do nonlinear dimensionality reduction. I'm like, okay, that's exactly what we need. We have those nonlinear patterns and nonlinear structures in the input-output relationships, and we're trying to capture those. So let us take this approach, okay? So this is L, our loss function we're trying to optimize, okay? And we're gonna approximate this function with a superposition of 2 functions, psi and phi. Phi is going to be our Gaussian process, the same surrogate that we used before. But now before we send it to this surrogate psi, we're going to apply this psi function, which is a deep learning. And the goal for deep learning model is to reduce dimensionality. So remember, Gaussian process doesn't work well in high dimensions. So what we're going to do, we're going to reduce dimension, and then we're going to send it to Gaussian process. And Gaussian process will do what the Gaussian process does well. And so we basically just add this new function to our setup, and we try to approximate this loss function as a superposition of dimensionality reduction in the surrogate. Okay, and we just the same way we learn Gaussian surrogate from the input-output evaluations, we're going to learn this guy from the same pairs of data. So we're going to run our simulator several times, and we're going to try those nonlinear dimensionality reduction patterns that are present in the input-output relationships. So this is our setup. What we do first, we take the input. This is our original inputs theta that comes into ABM, right? And then we have these pairs, you know, inputs and outputs. This inputs to the simulator, this is outputs to the simulator. And then we calculate a neural network that consists of two parts, the projection part and the surrogate part. So the projection part just takes the inputs and produces low-dimensional version of those inputs. And then you have this surrogate part that takes the low-dimensional version of your inputs and tries to feed into the function that you try to model. Okay? And then, okay, the biggest problem with neural nets is uncertainty quantification. It's hard to get, you know, if you deal with stochastic situation and you try to get uncertainty bounds in your prediction, neural nets don't give you them. So what we do a very simple thing. We take this neural network part, second part of our neural network, we throw it out, and we substitute with Gaussian process. So we build Gaussian process in low-dimensional space that was identified by deep learning model. Are you guys following?
Could you repeat what you just said? I'm sorry.
So essentially, we build a model at the end. So this one is a deep learning model that takes their inputs and produces low-dimensional version of inputs. So it's just a function that takes d-dimensional vector as an input and produces n-dimensional vector as an output. Okay, this is some nonlinear function here, and n is less than d. That's our goal. Our goal is to make the dimensionality smaller. And then what we do, we build the deep learning, we build the Gaussian process surrogate in this low-dimensional space. So we still approximate the function that we want to approximate, the same as you saw in the taxi, right? But now we just do it in this, in machine learning they call it feature space, or latent variable space, or whatever you want to call it.
Mm-hmm.
So some projected space of your original inputs. Okay?
How do you know how well you have reduced your dimensionality? How do you know that what you threw out is not that important?
So that's a good question. So we actually tested at this stage. Unfortunately, there is no. It's in statistics called intrinsic dimension. Intrinsic dimension means so your original inputs are t-dimensional, but you know intrinsic dimension is n, and n is hopefully much smaller than d. And to know exactly what n is not an easy problem. There are automated ways to do it in Bayesian statistics. People try to. We're going to explore them. Actually, we have a collaboration now that we try to automate the process of identifying this intrinsic dimensionality n. But for now, we just do it empirically. We try 1, 2, 3, 4, 5, 6. Those things are very fast to feed. So I can do 20 of those models on my laptop in 1 minute. So I just try all possible dimensions, and I see which dimensions gives me the basically smallest misfit between the target values and what my model is actually predicting. So misfit tells me how well I capture this low dimensional structure. And
I'd be really surprised if you can find any theoretical breakthrough that does better than that empirical approach.
well, I have collaborators that claim they do. It's actually so people work on it. We particularly don't, but people do. So
just real quick, you lose the interpretability of your features.
oh yeah. Those are nonlinear functions. So
Okay.
nonlinear. Yeah. So yeah, those are like some. Yeah. Yeah. You cannot say why change one unit in this psi one. What does it mean? You don't even know what units they're measured in.
Mm-hmm.
So you lose interpretability.
So I assume that one way you could do this would be to just using an autoencoder decoder, and then you just throw away the decoder part that confirms you had the right amount of dimensionality reduction,
Yeah.
and just use the first half of it to go further.
So we're gonna do it exactly that actually.
Okay.
Yeah. So it's coming.
Okay.
Yeah. That's a very good insight. That's a very good insight. Okay. So I have a few slides about deep learning. I'm gonna skip them. If you guys are interested in deep learning, there's a whole bunch of things online about deep learning. I probably should talk about Kolmogorov-Arnold. Yeah. So it's basically so the theory of deep learning. Talking about theory, there's not much theory. Okay, actually, there is a lot of theory, but there's no theory that is applicable. Okay. So there are a lot of theoretical results that kind of make you feel good about neural nets. Give you warm feelings about them, but nothing that actually you can go and get some guarantees for your specific problem. So there's no guarantees for whatsoever. So one of those theorems that gives you warm feeling, and actually this one that actually inspired a lot of people who do theory on deep learning. They use this as like a starting point. This Kolmogorov Kolmogorov representation theorem that basically tells you can take any multivariate function f and you can represent it as a two-layer neural network. And it's not approximation, it's exact representation. It's called representation theorem. So the claim is that you can exactly represent any function f with two-layer neural network. And this two-layer neural network, so it has this function psi. I apologize for collapse of collision of notations. And those psi's are univariate. So it's a univariate functions, and then you weigh those univariate functions. So it actually looks very similar to how modern neural networks look like. The only difference is those things that are called activation functions. You have multiple of them. It's not the same activation function. And the way they construct those activation functions in the proof is they basically have this infinite dimension. It's like a fractal structure they built, and then they show that you basically take a little piece of this fractal and you can precisely represent your function inside this little piece of fractal. But it's infinitely divisible object, which is not computable. So this theorem doesn't lead to any practical algorithm that you can compute, and those functions are different from activation functions people use in neural networks. So it's even from that perspective, it's not very usable. And also, it was actually shown by the Trushkin later in 1967 that those functions are discontinuous. So he actually proved specific property that those activation functions are discontinuous. And activation functions we use in modern neural networks are continuous functions. So it's basically, it's kind of look like neural network, but still if you like start zooming in, it stops looking like a neural network.
It's awfully hard to optimize when you've got discontinuous control variables.
Yeah, so that's one of the reasons. Yeah, so I think people experiment like in 80s trying to do this activation function. There were papers that say, okay, we don't really have to have those sigmas that have this nice properties. We can have more complex machines inside the neurons, and it didn't go anywhere. So yeah, and probably because of the optimization algorithms actually. So optimizing, yeah. So I'm going to skip Kolmogorov-Arnold examples. I just going to, this is summary, sorry. Any functions can be represented using deep learning. Two-layer can represent any Boolean operation. So you basically can take your computer code and you can run, you can write it as a deep learning model. So if you think of ABM model as a computer code, you actually can represent ABM model as a deep learning, okay? So any convex polygon can be represented by two-layer neural net, and three-layer gives you any polygon, non-convex and discontinuous polygons, and a fine transformation for a single nonlinear function give you approximation to any smooth function. Okay, so it's a very powerful approximator. It's a very powerful pattern matching machine.
I thought it took 3 to represent an exclusive OR.
Exclusive OR is. No, I think you need 2 layers because exclusive OR it's and then OR applied to it's like and OR and then not applied to it.
Right.
So you can apply and and OR in one layer and not in the other layer. So it takes I think it's 2 layers. As far as I remember exclusive OR. But you basically have to write down and see how many layers you have. Maybe 3. Maybe exclusive OR is 3. But no, actually pretty sure it's 2. But we can write down exclusive ORs.
Minsky and Papert against perceptrons.
So that was this. It was way before I started being interested in those problems. So to me, it's an ancient history. But they just
Some of those are old enough.
but yeah, some of you people remember this. Minsky, a very influential computer scientist who claimed that perceptrons will never work, and perceptron is the simplest version of neural network. 2 layers. So he actually showed a bunch of examples where this machine fails, so I guess it's one of those things that influential people can do. Once they say something, people basically take it for granted, and so the research in this field was not very active until 2012, right? 2012 when we started having this renaissance, when Google's and Facebook started investing money into those machines. And then universities realized that. So I teach deep learning course now. So it's becoming like a commodity nowadays. So something that was like just something that a small group of people use very exclusively is just becoming like a machine that is everywhere. So this is type of network we use. We use those Rayleigh networks. So what Rayleigh network does is actually just splits your input space. So if you're familiar with tree models, decision tree models, right? Decision tree models split your space, and they use the splits that go parallel to the axis, right? So you remember tree just splits it like this, right? So neural network also does the split, but it can have hyperplanes as splits. So just a little bit more flexible splitting machine. And then you can combine those splits. This is the depth of the architecture. So imagine, you can have two splits in one layer, and then on the next layer you can have a result of those two splits. So you can build combinations of splits. So you basically have this exponentially growing complexity of your geometry as the depth goes, versus if you do it in one layer, your complexity of your geometry grows linearly with a number of neurons in one layer. So and so this is first example, very simple example. We have a 100-dimensional function, so a function that takes 100 inputs. So this vector x is 100-dimensional. And then the function goes like this. You basically take the dot product with some vector u, and then take absolute value. So this is a univariate function, okay? And this univariate function of 100-dimensional input, but there is one-dimensional structure essentially, right? Because your function is constant along this certain direction, okay? And then I add some noise, and then I give this data to neural network, and I ask this neural network to identify this one-dimensional structure, and it actually can identify this one-dimensional structure. I don't tell exactly what the form of this structure is, so neural network just learns it from the data. Okay? So the blue line is the pattern that neural network learns, so it learned this one-dimensional representation of the data. And then we tried a little bit more complex example, right? So we had some linear structure in the first example. This is nonlinear structure. So this is my data. I basically have zeros everywhere, except for those two semicircles. And I want neural network to basically learn representation of it in low dimension. And if you remember Rayleigh network, what Rayleigh network does, it basically cuts your space, and then can take one of the cuts, and then it can rotate it and stretch and shift. So that's kind of transformations I can do to my space, right? And I'm not sure, but I think you cannot put it into one dimension. So you can go home and you try to cut it, stretch it, rotate it, and shift, and I don't think it's representable in one dimension. Okay? So we cannot really represent it in one dimension. We tried neural network. We asked neural network to represent in one dimension. So it's actually learned pattern reasonably well. But so this is our projected space, x projected, and this is the value of the y. And you see there's overlaps, right? So for this value, you can be here or here. So it doesn't really segment very well. It doesn't really learn one-dimensional structure. And again, as I said, by using those transformations, you can unlearn this one-dimensional representation. But once we ask it to represent two dimensions, it actually does a nice thing, right? So it actually separates the values of y nicely. So it basically moves those points around, so that points of one color are separated from each other. And even though I didn't reduce dimensionality here, I went from two-dimensional space to two-dimensional space, but I achieved something else here. I achieved here much better representation of my relationship between the inputs and outputs. And representation it's linear now. So if I want to build a surrogate, for example, if I want to build an approximator, I can just build two lines. And I can build very simple approximator to this input-output relationship. So in this projected space, I can build simpler surrogate models that I understand. Even though my projections I don't understand anymore, right? Back to your point. But I can understand it. And I can build Gaussian process surrogates now also. Gaussian process surrogates also assume some stationarity in the data. This data doesn't have that. So my Gaussian process won't work for this data set, my Gaussian process will work for this data set. So even though no dimensionality reduction has been achieved, but some nice properties were derived from the input-output relationships. All right, so I have a few more examples. I want to skip those. I want to go back to the ABM models. So this is my strontium-90 transport simulator. So I just did this trick I explained to you. I took this 20-dimensional input space, I projected, I think, into 5 dimensions. And then so this is my surrogate built in the original dimensionality, and this is my surrogate built. This is my y, and this is prediction by the surrogate. So now we actually have meaningful predictions and meaningful uncertainties about those predictions. So actually can build surrogates now, which are good surrogates and give good predictions in those low dimensional spaces. Okay. So this is back to your point. You remember when we do Bayesian optimization, when we try to optimize on top of the simulator, we do the sequential design of experiments. So we evaluate at some point. So we give inputs, simulator produces outputs. We take those outputs, and then we decide what next point we wanted to evaluate at. Right? It's basically any optimization algorithm works like that. Even if you take gradient descent, right? Gradient descent goes to this location, calculates the gradient from this location, goes in the gradient of this direction. So it's always the sequential search in the input space. Okay. So, but now our surrogate lives in this low dimensional space, but we cannot do the search in this low dimensional space. If we calculate the next point in this low dimensional space, how do we evaluate simulate in this low dimensional space? We don't know. So we have to go and do reconstruction. So then we build this autoencoder type of structure that takes the low dimensional representation, reconstructs it back to high dimensions, and then we can do the sequential search in the input spaces. So we can do optimization algorithms on top of it using the reconstruction algorithm.
Sorry, and are there conditions on when this is an invertible function?
It has to be invertible.
Right.
It got to be invertible. Otherwise, we cannot.
Sure, exactly.
Yeah.
But are there conditions on that?
So the conditions are, if you truly have this intrinsic low dimensionality, then this one is invertible. Okay. So if this is truly low, if you don't basically lose much of information by going from here to here, then your reconstruction is going to be basically as good as loss of your information from here to here. But if you do lose a lot of information, if you pick n too small, right? Sometimes you might actually do good predictions from this small n, but reconstruction. Now you have to, when you try to identify n, you have to think of two things: how well you can reconstruct and how well you can predict. So that's a good point. But it's empirical. Something we look at this empirically. We just try to find those and this is basically the loss function we use to find to feed the whole architecture. So everything here is trainable. Everything here we can calculate gradients of every single piece. So we can do gradient descent on the whole structure, and we can find parameters of every single block in this diagram. And this is the loss function that we use at the end. So we basically try to balance the reconstruction quality. So you remember, this is compression and this is decompression. So this is how we reconstruct, and this is approximation quality of the function. And we have some weighting parameter lambda that tells us how much we want to weight one versus another, and we find n basically that gives us the lowest value for this loss function. So now we have to balance those things. And there's some math about Gaussian process that we can build Gaussian process in low dimensions. We can deal with constraints because we have a lot of times we have constraints in certain parameters have to be in certain ranges, and when we reconstruct it, we want the reconstruction to be inside this range. So we can deal with constraints. So our reconstructions become part of the ranges. So here are a few results, the very preliminary results that we have for agent-based simulators using this machinery. So we applied it to the Bloomington model. It's a town in Illinois, southwest of Chicago. And we basically, what we have right now is, the bottom line, we have improvement by doing dimensionality reduction versus vanilla Gaussian process, okay? So we can find better solutions and we can find them faster, okay? But this is very preliminary stuff for now. So in order for us to scale it to go beyond those small simulators, we actually have to move to HPCs. So, and my student Laura, who is doing most of this work, she's actually going to be at Arden in October, and they will start moving those things to HPCs, and then we'll be able to scale those things and see how they work at large scale models rather than those toy models that we can run many times on our laptops. Okay. So Gaussian process is practical in high dimensions when combined with dimensionality reduction techniques. Deep learning shows good empirical results and benchmarks and practical IBM problems. And hopefully we can solve complex and important problems which are large scale and people use actually in practice. That's all I have.
Going back to the question I asked about the taxi model, that that result for 50 is far enough out of the curve of the others to lead me to suspect there's a latent variable of some kind. Maybe something like where there's a small number of taxis, they're well coordinated, where there's a large number of taxis, improvisation works, but somewhere in between is a bad spot where they're competing with each other.
Yeah.
And it's
Yeah,
damaging.
yeah, it's exactly, yeah. So on this trade-off, you basically have, when you have too many taxes, you always have revenues coming. And when you have too little taxes, you don't lose too much money. But in the middle, you kind of and lose and don't get rid of it, you know. So that's, yeah, somehow, when you, effect is non-linear basically. But, yeah. And that's the whole point, that this whole relationship between inputs and outputs is very non-linear. And there are interactions that happen inside, which we don't really, understand, and trying to capture them is not easy.
Yeah, can you say a little bit more about how you look for the latent variable when you see something like that? You know there's got to be one. Now, how do you look for it?
Well, one of the claim of fame for neural nets is that actually that's how neural nets are sold by machine learners, is that they identify those latent variables automatically, right? So standard, if you standard way of building predictive models is that you sit down and you think about those interactions between the input variables, and you introduce new predictors that are, like interactions between the predictors, and then you put it into some linear model or some, polynomial function. Neural network is supposed to automate this process, so it's supposed to extract those interactions and those dependencies by just looking at the data without model and telling what those are, by hand.
What if, again, down to one dimension, you've got a fairly sharp peak, and further down you've got a much flatter plateau, not as high as the sharpest peak, but if you have enough uncertainty that you're not always going to be on the sharper peak, the plateau is a better solution for you.
So if I have
it's
enough uncertainty,
less sensitive to variation.
if I have
You
enough
find
of
that?
uncertainty on the plateau to justify going and exploring the plateau, I will do that. So that's basically my search algorithm, my optimization algorithm does that. It balances, exploration and exploitation by saying, okay, there's, I know there's a good solution here, and I know there's like solutions look bad here, but the uncertainty is so high, so there is a chance I might have a good solution here. So the algorithm will go there and explore the space with high uncertainties. That's how optimization algorithms are set up. It's basically exploitation, exploration, process. Yeah, that's a good point. Yeah.
I've flirted with the same idea using the Delany interpolation. Kind of left it pretty quickly because I realized that in order for any of these algorithms, optimization algorithms to work, you have to have enough of the space covered
Correct.
to make the next prediction.
Correct.
Which is the part where it gets expensive in running large scale ABMs anyway.
Correct.
Do you have an idea for in order, at least from your initial results, how much of a space I would need to cover in order for me to begin making predictions for the outputs from certain inputs?
I don't, but one thing which is good about Bayesian approach is that you can put priors. And what priors are is basically a model's intuition about what are the good sets of parameters are. And you have a very natural way to take those priors, write them down as probability distributions about your inputs, and it can be joined, for example, and then use those to do the search. So your search is going to be biased towards your priors, essentially. Okay, but giving you a specific about I don't think there's general answer. So it's basically how well you can define your priors, and how much of the structure you have in your model. Because you remember, it's actually, so high dimensionality is not that big of an issue. If you have n-dimensional space and your relationships are linear, I just need n points to fit the hyperplane in this space, right? Like in 2 dimensions, I just need 2 points. So when relationships are simple, I can live with smaller samples to identify those relationships. The problem is when dimensionality is high and relationships are not simple. So, and this is like, how do you quantify the complexity or simplicity of the function, right? Okay, linear is very simple, and then you basically, so like what people do in neural networks, for example, recent papers, the way they try to model complex functions, basically functions with zigzag, right? A number of zigzags or number of peaks in the zigzags will be the complexity of your function. So complex function with a function with many zigzags. So if you have something like that, then doing any of this local search is going to be miserable exercise,
Yep.
right? Because finding the peaks, you basically have to be near this peak, and to be near peak at high dimensions is hard. Okay. Yeah. So I guess that's basically how complex your relationships are and how good your priors are about what your good values of parameters to be as a modeler. So those two things combined will tell you how well you can explore the input space efficiently.
So expanding on that real quick, if no one else has any questions, does anyone? So, but the dimensional space for an ABM in many ways defines a single dimension redefines the whole space. So I like the example that you gave earlier about how uniform in three-dimensional space collapses. So I think of high dimensionality as a soap bubble, right?
Yeah.
Uniform distribution in a sphere as you move outwards is not the same thing as a uniform distribution on a piece of paper on a 2D,
Right.
right? So dimension changes the space of behavior of a model entirely.
Right.
So my question here is, all of these techniques involve the reduction of the dimensionality in some way,
Yeah.
right? Again, is it so reduction of the dimensionality in some way, and then the other thing is we don't know how much of the space we're covering. So again, how can we know that deep learning works for any model if we neither do we know the interpretability of the dimensions, the space itself, or how much of the space to cover?
Again, in my application, it's just how well you can predict. So
All right,
there's,
fair enough.
yeah.
If it works, then it works.
Yeah, in,
Yeah.
like in the world I live, and basically it's so and this is not a small world. Every metropolitan area of population more than 250,000 will have this type of model in place. So there are dozens of those models in the country, and each city will spend millions and millions of dollars, every few years updating those models. So that's just even if you capture this one. So maybe I shouldn't call it ABM, right? Maybe I should call it ABM and transportation. So being very specific about my application. But in my world, yeah, prediction is kind of the is the certificate, if you wish, of me being right. Yeah.
Fair enough.
I think there are lots of other areas where the approach is also the right one or the best one you can do. When you're using prediction as your criterion, what you do with a bunch of simulations is get some points, which if you had enough of them, you could make a response surface. Suggestion: if you know that there's a certain given amount of uncertainty you can't get below,
Yeah.
look for patches
Yeah.
with that amount of uncertainty
Yeah. That's a good point
rather
to
than
that.
points,
Yeah.
and consider only the parts of that response surface space where you don't see enough jaggedness
Yeah.
to make a patch infeasible to find. That cuts down your search a lot.
Yeah.
Patent pending.
Well, and so Gaussian processes actually do that. They give you this uncertainty quantification. So you can ask this question once you start exploring your space, right? And you try to build a surrogate in the space. Your surrogate knows what regions of your input are the regions to be explored more.
Mhm.
So you can set up. Basically, you can calculate it from your surrogate.
Sure.
So those uncertainty bounds can be calculated in high dimensions as well. So it will tell you I'm most uncertain here, and you can go and explore here. So just Gaussian process surrogate itself gives you the sequential design of experiment, which as I said, it's probably a much more efficient way to explore the input space, regardless of dimensionality, than latent hypercube or any type of random sampling. Just because again, once you start observing, there's nothing changes when you vary those combinations of inputs. You stop varying them. You say, okay, I'm pretty certain what happens in this region, right? So you start moving to other regions of the input space. So yeah.
So because most of us in the room don't have much experience with the Gaussian process simulator, is there like standard software in R or Python?
R probably has like 5 or 6 different libraries.
Okay.
Yeah, if you type Gaussian process R, there are a few of them.
You guys write your own when you do it, or how do you?
We work with a person from Virginia Tech, Bobby Gramsci. So we use his packages. So if you type Bobby Gramsci R Gaussian process, you'll find that. And in Python, we use gPyTorch, which actually gives you nice integration with PyTorch, which is deep learning framework. So what we do in Python, actually, we take Gaussian process and neural network, combine them, and then we can do back propagation, so we can learn the whole system together rather than learning separately. So it allows, GPyTorch allows us to do that. But there is GPy I think is the most famous one in Python. So GPy Python, and Bobby Gramercy has his for R.
Now, how about if I have multiple performance measures, so phi is not a scalar? Do I have to basically just put weights on there to make it a scalar?
So yeah, you can put it into scale in this way. There are techniques for doing multiple Gaussian processes.
Okay.
The problem becomes when you have correlation structure. When there is no correlation structure, you can model them separately. So you can basically slap Gaussian process in each of your phi's, right? But when you start having correlation structure in those, then it becomes tricky. And this is another area where it's like a Wild West. So there's like every person who works in Gaussian process has its own little technique of. I don't think there's like a gold standard for it, for dealing with, and it's very problem specific. So some problems people try to use some spatial decomposition to decouple them and just say, okay, in this space we're gonna model. But my favorite actually, and the most stupid one, well, not stupid, but it's very good. So you have this multiple outputs, and what you do, it's actually Dave Higdon also from Virginia Tech. So he suggested in 2012. So you run your simulator many times, like 30 times, right? And you build matrix of your outputs, right? So each output is a vector, and you have 20 columns for 20 runs. Then you do principal component analysis on it, okay? And you find those principal components in this output space. So not in the input space, but in the output space. You find principal components in the output space. And then you say, okay, every output of my simulator is a linear combination of those, like 5 principal components. But the weights, instead of being constant, are single varied Gaussian processes. So you have 5 single, so basically that's how we decouple this correlation structure. The correlation structure will be captured by taking linear combination of principal components built on the outputs, and the weights of the principal components are univariate Gaussian processes. So yeah, if you ask me, I would probably do something like that. I would use that approach.
And then how do you get from that back to telling somebody what policy would improve the outcome?
What policy would improve the outcome? So in our case, we solve it using optimization techniques. So we just run the Bayesian optimization that uses Gaussian process surrogate underlying to solve the optimization problem. The same as I showed with taxa, right? So you basically take your plot and you optimize Gaussian process rather than optimizing the ABM box itself.
But you're down to considering all candidate solutions and comparing them. There's no shortcut that says this way is up.
No, we don't have gradients. Yeah.
Yeah.
So it's a derivative-free optimization, and it's again there's a whole bunch of techniques. If you ask applied math people, they say you need to do quadratic approximations locally. If you ask statisticians, they say you need to use Gaussian process. If you ask computer scientists, they tell you evolutionary algorithms. So it depends on who you ask. They'll tell you good answer for how to do those things. So I use answer that comes from statistics community. It seems to work for us, but evolution algorithms I'm sure will work as well. Yeah.
Can we tell if there are any questions online or
No.
Okay. So why don't we stop here, and if there are any further questions, you can ask Vadim afterwards. Thank you, Vadim.